Hello everyone, welcome to Science Breaks, a lecture series by Imperial College showcasing the exciting research conducted at the institution. Now, today we've got an amazing speaker. We have Professor Roberto Trotta talking about from Big Bang to AI. Now, before I get started, I'd just like to point out that you can submit questions at any point using the Q&A screen at the side of the screen. The event is being recorded, so if you would like to remain anonymous, please do so. You don't have to submit your name, and you can, if you like a question that's been submitted by anyone else during the speak, please use the thumbs up section during that, and that will allow us to see which of the questions are most popular. There will also be a break at the end of Professor Trotta's talk where you can have grab a cup of tea, and also you can still continue submitting questions through that. Now, I'd like to welcome Professor Trotta today, and we're going to be talking about, as I say, from the Big Bang to the AI. At the beginning of last century, the Nobel Prize winning physicist Ernest Rutherford reportedly believed that if your experiment needs statistics, then you ought to have done a better experiment. Yet today, advanced statistical methods belong to the toolbox of every cosmologist, and artificial intelligence, AI, is poised to change how we look at the universe. Now, last year, Professor Roberto Trotta gave his inaugural lecture and discussed how astrostatistics will meet the challenges posed by big data to help answer fundamental questions of the cosmos. What is the universe made of? How did it all begin? And what is its ultimate destiny? And you can watch this lecture online. Now, in this latest event here today with Science Breaks, Professor Trotta will expand upon his inaugural lecture discussing how AI and machine learning are helping us hunt for dark matter. He will also delve into the latest research on dark matter, which is lurking at the centre of our galaxy, the Milky Way. We're going to look at what do we know and how do we find out more. Now, I'll give you a brief introduction to our speaker today, Professor Roberto Trotta, one of my colleagues at Imperial College, and it is a real pleasure to introduce him today. Roberto is a professor of astrostatistics at Imperial College London, and his research in cosmology aims at kind of highlighting and revealing the nature of dark matter and dark energy in the cosmos, which accounts for 95% of the content of the universe. He's also visiting professor of cosmology at Gresham College. He was born in and grew up in the Italian-speaking part of Switzerland after obtaining an MSc in physics from ETH Zurich and a PhD in theoretical physics from the University of Geneva. He became the Sir Norman Lockyer Fellow of the Royal Astronomical Society at Oxford University, and a junior fellow of St Anne's College before being appointed to Imperial College in 2008. Now, as I'd like to point out, Professor Trotta is not only an experienced and excellent scientist, he's also an experienced science communicator, and he's looked at novel ways of making abstract concepts in cosmology more tangible to the public at large. And he's actually done this in a number of different ways. He's collaborated with chefs in a tasting experience, which I was lucky enough to go through, which was absolutely fantastic. And he's looked at human-machine interactions. He's the recipient of numerous awards, and I was going to say I could go from all here. I won't embarrass him all there, but I know recently, because I had the great pleasure in nominating for it, he was awarded the Annie Maunder Medal from the Royal Astronomical Society. He's also is the recipient of several President's Awards at Imperial College, and he's also written an award-winning book, The Edge of the Sky, which explains the universe only using the most common 1,000 words in English, for which he was named one of the world's 100 global thinkers in 2014 by Foreign Policy magazine. Outside of Imperial, Professor Trotta is director and co-founder of Data Fusion Consultants, offering data analytic solutions derived from his research. Now, that's enough of me speaking there. So I think I'd like plenty of you would actually like to hear Roberto speak. So it is with great pleasure that I hand over to Professor Roberto Trotta and his talk From the Big Bang to AI. Over to you, Roberto.
Thank you, Simon, for this very kind introduction, and welcome everybody, wherever you may be today, for the Science Breaks lecture. And I'm very excited to be following up on my inaugural lecture from last January. Of course, the world has changed immeasurably since, and we can hardly recognize it today. AI and dark matter research have not stood still in the meantime, and I'm excited to share with you some of the latest news and developments in this fast-paced and very interesting, for me and I hope for all of you, field where we are trying to use artificial intelligence, machine learning, statistical methods to learn more about the fundamental nature of what the universe is made of. Going back to my lecture, I then argued that there is a virtuous circle between astrophysics and cosmology on one side and AI, artificial intelligence, and machine learning on the other side, with problems in astrophysics and cosmology giving interesting challenges to AI today, and vice versa, AI giving us much needed tools, indeed indispensable tools, to understand the fundamental nature of the universe. And together, these two sides of this circle are leading to major advances in research, education, and even societal applications of the methods that we develop in cosmology to solve our astrophysical and cosmological problems with AI, but that can also be method that can also be used in the real world in very concrete applications. To go back to cosmology, just to delve into the universe as we know it and to get a sense for the scales that we are talking about when we talk about cosmology, here is a picture of the sky that you may be acquainted with in terms of the size of the full moon, that it's depicted here to scale to give you a sense of proportion. But really, when we're talking about cosmology, we're talking about something almost entirely different. We're talking about something that lurks inside the little yellow square, rectangle that you see at the center of your screens. And that square or rectangle is so small as to fit inside the eye of a needle held at arm's length. And it doesn't look like much at all in this picture, but if we zoom in by using the Hubble Space Telescope, this is what you see. Inside that small eye of a needle lurk up to 10,000 galaxies. And if I zoom in further, you can see them in all their glory, each one of those dots being an entire galaxy made of hundreds of billions of stars. There are 10,000 galaxies in the eye of the needle. And that is the domain of cosmology. This is the universe that we are trying to understand by asking questions about its nature, its origin, and its destiny. But if you think that this kind of research today is done like this, middle-aged white man, perhaps smoking a pipe and looking through a big telescope at the night sky, well, this is a little bit passé now for at least two reasons. One is that this is a picture of Edwin Hubble in the 1950s, looking at the sky through his telescope. But if we only imagine astronomy, astrophysics, and cosmology being carried out like this, then we're missing out at least half of the story, namely the contribution, fundamental contribution given by women to the development of science, astrophysics, and cosmology in particular. Here is a picture of Vera Rubin, one of the co-discoverers, one might say, of dark matter. So very important to remember that history is not only made of white men, but also women and people from all over the world from many different backgrounds. But equally importantly, today, many discoveries in cosmology and certainly many of the challenges of cosmology are no longer about finding a new star or a new galaxy or even a new planet with a telescope in your backyard, although amateur astronomy is still very much important, but rather today, cosmology and astronomy are done like this, using space-borne, ground-based, and even observatories hidden in the ice cap in the Antarctic to look for signals in the universe that come with copious data. All of these multi-billion-dollar facilities beam back an enormous amount of data, and all of this data need to be collected, processed, and understood using a great deal of computer power. But not just the brute force of computational power is necessary. We also need to be smart. We also need to be able to understand what those signals mean and how to extract the faint signals that we're looking for example, dark matter. And that's where statistics and artificial intelligence come in. In summary, just to recap where we are after several decades of very intense investigations in cosmology, we now face the puzzle of a very interesting but very challenging universe, one in which only 5% of the universe is made of normal matter, of the kind that we saw earlier through Hubble, while 95% of the universe is dark and presently largely not really understood. 25% in the form of dark matter, perhaps a new kind of particle left over from the Big Bang, and an incredible 70% made of dark energy, an even more puzzling component of the universe that is responsible for its acceleration in the last 6 or so billion years. And today I'd like to share with you some of the latest developments in our search for dark matter. How close are we to solving that mystery? We know dark matter is out there through the work of Vera Rubin and many others. We have seen it in the sky through its effect through gravitation on the formation and movement of galaxies, among others. Can we find out what dark matter actually is, and how can AI help in this quest? We can safely say that we have entered the era of big data in astronomy. Here, this graph shows the number of astronomical objects known to mankind as a function of time. And you can see that things didn't change much for several hundreds of years, even after the invention of the telescope in the early 1600s, until the early 2000s, when a big technological major advance came into play, namely CCD cameras, the same kind of cameras that you have inside your mobile phones that allow us to take many more pictures much faster of the sky. And nowadays, with space-borne observatories, for example, the Gaia mission, we are able to measure the position and properties of billions of objects in the sky. So a truly exponential increase in data. But data is not enough. Data is only part of the answer. Data, in fact, are useless unless we also have the means of understanding what they mean and extracting the answers to the questions that we have. And that's where machine learning and the AI come in, because you can see in blue the era of big data in terms of interest over time is flattening out and is being taken over by the era of machine learning. Those are systems designed to work with those big data that use the information in the data to come up with interesting new insights about phenomena of interest, in our case, dark matter. And so our approach has been for a number of years, and is accelerating still, to take all of these different probes that we have with dark matter from the sky and the Earth, colliders and other detectors that we have on Earth, all looking for dark matter, and put them all together using machine learning and now AI in order to find a way of zooming into dark matter. A puzzle that remains very much unresolved, and I'd like to share with you now some of the latest developments in this area. So our story about looking for dark matter in our own galaxy starts with this view of the night sky. Now, this is probably not the view of the night sky that you're lucky enough to have in London ever, because it does require a very dark night, which London unfortunately no longer enjoys. However, if you are in a dark place in the northern hemisphere tonight, just after sunset, you can't miss two very bright spots on the southeasterly horizon, rather, Saturn and Jupiter. And which are the two bright spots here on my slide. And if you draw a line through Saturn and Jupiter towards the crescent of the moon, and you join them up together, you will pass not far off the galactic center, which is the little circle with crosses in this slide. The galactic center is the center of our own galaxy, the Milky Way, which shows up in a very dark sky, as many of you perhaps have been fortunate to see with their own eyes, as a streak of light going through the sky, and it's made of millions and billions of stars, which are too small to be seen with the naked eye, but altogether give you a little bit of a cloud, a beautiful, magnificent impression, like powder of diamonds scattered on the sky. So if you are lucky enough to be able to see the sky tonight, then look for the galactic center. And this galactic center is where we think, well, lots of interesting things happen, but also where we think in our galaxy, most of the dark matter is concentrated. So let's take a closer look to this galactic center. We're going to rotate ourselves in such a way so that the Milky Way now is an horizontal streak in the sky here. And we're going to look at the Milky Way not with optical light, like in this picture, but with higher energy light, gamma rays. Fortunately, we have a satellite up there, the Fermi-LAT satellite, which has been mapping the gamma ray sky for several years now, and it has produced this beautiful map of the sky in gamma rays. Now, gamma rays, we cannot get them on the Earth because we are shielded from the atmosphere, thankfully, because they're very damaging for organisms. But from above the atmosphere, we can get this picture of the sky, and the part of the Milky Way that we saw previously is inside this rectangle. Now you can see from the bright streak of light in the center of the picture, there's lots of gamma rays coming from our galaxy. That's because gamma rays are emitted by stars and hot gas that have nothing to do with dark matter, but emit this kind of very powerful, very energetic light. However, according to some theories about the nature of dark matter, if dark matter is sufficiently concentrated, dark matter particles will collide with each other, and in doing so will annihilate, will destroy themselves into, among other things, high energy gamma rays of the kind that we can see with this satellite. So one promising venue for trying to detect dark matter is to look for dark matter from the galactic center, looking for gamma rays coming from dark matter particles lurking and colliding in there. And several years ago, indeed, an interesting blob was found at the very center of our Milky Way, which is the red blob in the right-hand side, bottom right-hand side of this picture. Observations from Fermi, when massaged with statistics and other methods, showed an excess of gamma rays from the center of the galaxy. And as you can see from the top right square in the picture, this looked very similar to what was expected from dark matter. So was it the case that dark matter was indeed lurking at the center of the galaxy, and those gamma rays were the telltale sign of its presence? If so, this signature of dark matter would tell us that dark matter is a particle quite heavy, about 10 times or more heavier than a proton, so quite a heavy particle. However, over the years, this evidence has come and gone. Other analyses have found other effects and have concluded that instead of being due to dark matter, this excess emission of gamma rays was due by more mundane astrophysical phenomena, like pulsars, for example. And so it hasn't been really clear whether or not these extra gamma rays were due to dark matter or not. And the debate is still raging. We're not really sure. Unfortunately, the galactic center is tens of thousands of light years away. We can't go there and check. So perhaps we thought there's another way of looking for this dark matter signature in the sky by looking at a quieter spot in the sky, a spot that's not so messy, not so complicated as the galactic center, a spot where dark matter could be seen more easily. And so one such spot are satellite galaxies of the Milky Way called dwarf galaxies. Now, I hope you can see the galaxy at the center of this picture. Or can you? Well, probably not, because, well, I can't see a galaxy either. Certainly not a beautiful spiral galaxy of the kind that we are used to seeing in the beautiful Hubble pictures. But I assure you, there is a galaxy lurking in here, except it's a dwarf galaxy. It's a galaxy that contains only a few thousands of stars rather than the hundreds of billions of stars of normal galaxies. And if I clean up this picture, this is the galaxy. Just this smattering of dots, the few stars that make up this galaxy. It's a very dark galaxy. It's a dwarf galaxy orbiting the Milky Way. Now, these dwarf galaxies are very, very interesting because they wouldn't exist unless they were kept together by dark matter. So their very existence, in a sense, is another indication of the presence of dark matter. But what is also exciting is that because there are so few stars in these dwarf galaxies and so little gas, any gamma ray emission from those dwarf galaxies ought to come from dark matter. There's almost nothing else in here that could emit gamma rays. And therefore, if we look for gamma rays from these dwarfs, so went the idea, it should be possible to detect dark matter, the invisible halo of dark matter that keeps the galaxy together. We reckon 3,400 times more dark matter than normal matter in such galaxies. So this idea has been exploited in the past, and myself and my collaborators did a more recent analysis last year where we looked at not one, but 27 such dwarf galaxies looking for dark matter signatures, and we found none. So we concluded that those galaxies did, while having dark matter inside, they didn't show the same kind of signature that dark matter would have given off if the dark matter in the galactic center was responsible for the excess gamma ray emission in the galactic center. In other words, the dark matter signature from the galactic center did not find corroboration in the dwarf galaxies, which was a really disappointing result. We were hoping to find it there. However, as always with dark matter, things are not quite as clear as they seem, because only this year we reanalyzed the problem in another paper which came out a few days ago, actually. And in this work, we revisited our calculations about how dark matter is supposed to be distributed in these dwarf galaxies. And what we discovered is that we and everybody else had previously missed a key ingredient about the way those galaxies form. And if we redid the calculation about how the dwarf galaxies form using the right physics, we discover that actually the dark matter content of these dwarf galaxies is much less than previously thought, which means dark matter can still hide away in those galaxies. There isn't enough of it to give off measurable signatures, measurable gamma rays, and therefore all of a sudden the galactic center excess is no longer ruled out. It could be indeed that the galactic center gamma rays are due to dark matter, and the fact that we don't see any dark matter signature in the dwarf galaxies doesn't rule it out. So you can see we're going full circle once again, and we still don't know whether to believe or not in the presence of dark matter in the Milky Way. So it's a really difficult problem, and it's a problem that keeps going back and forth depending on the new methods that we are able to develop to address this problem. So what are we going to do about it? How are we going to clear up this mystery? There are other ways. Instead of looking at the sky, why not look at the lab? Look at dark matter here on Earth, where we have much more controllable conditions, and we can perhaps detect the dark matter passing through the Earth, thousands and thousands of particles per square centimeter per second. We should be able to see them. And one such detector is the Xenon 1-ton detector, which sits at the bottom of the Gran Sasso laboratory in Italy. And this detector is put there for a very good reason. We need a very quiet place to look for the faint dark matter signal that otherwise would be completely swamped by other disturbances from other particles. So you can see the detector is inside the big cylinder, the big tank on the left. You can see two people on the right-hand side for scale. The actual detector is this bit here at the center. It's filled with over 3 tons of liquid xenon, the same kind of noble gas that powers headlights in fancy cars. Here it's used because it's got the right properties to detect dark matter. There's about $6 million worth of liquid xenon inside this detector. Outside the detector, there is a big shield made of water, purified water, again to shield the sensitive part of the detector from unwanted particles. Outside, other shields made of lead and other material, and of course all around it, rock, kilometers of rock, to put it in the most suitable place to shield away all other interactions and look for the faint whisper of dark matter as it passes through the detector. So the principle of operation of such a detector is that it just sits there quietly in silence and awaits for the rare event of a dark matter particle streaming through and hitting head-on a xenon nucleus. And that xenon nucleus gives off some light and some energy that can be detected by the sensors around the detector. And hopefully this will tell us that dark matter has passed through, and it can tell us something about the properties of dark matter, its mass, its characteristics. For years, these kind of detectors have been developed, some of them at Imperial as well, and they've been deployed, and despite various claims, nobody found anything that stood up to scrutiny over time, except just this summer, a very exciting new development, the Xenon 1-ton detector announced the discovery of 53 unexplained events that could be due to dark matter that apparently cannot be explained by other impurities or other disturbances to the detector that remain unexplained as of today. One of the possible explanations is dark matter. However, again, the mystery becomes even darker if possible, because if it was dark matter, then it is not the same kind of dark matter that would explain the galactic center excess. It would be a different type of dark matter, and therefore that sort of flies in the face of Occam's razor, the principle that the simplest possible explanation ought to be preferred. If it is dark matter, then surely we must require consistency between what we see in the sky and what we see in the lab. It's one particle, it ought to give similar signals. These 53 events cannot be explained this way. So you can see the quest continues. It's not over, but it's a very exciting time for dark matter research, because all this data are coming in. Machine learning and statistics are helping analyze and understand those data, and we are really now on trying to make shed some light on these mysterious events and these mysterious data. So what's next in the dark matter quest? We need more data, but also we need more powerful and more sensitive methods to analyze this data. Very soon, the Vera Rubin Observatory will start taking images of the sky, will produce a great deal of pictures and data from the universe looking for the effect of dark matter on galaxies, among other things. The Xenon 1-ton detector that I talked about will be upgraded to a multi-ton detector, being therefore much more sensitive in its quest for dark matter. And we will launch in a few years the Euclid Space Telescope, looking again at the effect of dark matter on the shape of galaxies, among other things in the sky. And all of these experiments together, and many others, will deliver a ton and ton of data that would need to be analyzed using advanced machine learning techniques that do not exist yet. Without artificial intelligence, without natural intelligence in the form of human creativity, we won't be able to understand what those data mean, and we won't be able to clarify once and for all the puzzle of dark matter. So I think all in all, it's a very exciting time for cosmology. It's a very exciting time for dark matter research. It's a very exciting time for machine learning research in astrophysics, and the quest continues. And I very much hope to be able to share with you soon some new discoveries that will clarify this amazing puzzle once and for all, 80 years after it was first formulated. This is all from me for today, but before we go into a short break, I'd like to announce and remind you of the competition you can now take part into. It's a competition to win a signed copy of my book, The Edge of the Sky, a little book that explains cosmology and everything there is in the universe using only the most common 1,000 words in English, and universe is not one of them. So it's called The All There Is. So to get your chance to win a signed copy of the book, please enter the competition. The link is being shared on the chat and will also be emailed to you after the event. And I very much hope that you will follow me on the tracks of dark matter by entering the competition. Now we'll have a short break, a few minutes, and we'll be back in about 3 or 4 minutes with the Q&A, and I look forward to hearing your questions. Thank you.
Thank you very much, Roberto, for an absolutely fascinating talk there. Now, we've had quite a few questions coming in over the break, so I'm going to try and read out some of the most popular ones, and hopefully you'll be able to answer them or give us some insight into them. So the most popular one we seem to have at the moment is from Lan, who says, most people have no idea what cosmology means and don't see how it relates to real life, apart from outside things like science fiction movies. What ways are there to bridge the gap between science and real life and to create opportunities for normal people to benefit and use your research outside of education and entertainment? So I don't know if you'll be able to kind of expand on that or answer that, please, Roberto.
Thank you, Simon. Thank you for a great question. We could spend a long time talking about this, but I think there are at least two. There are many more, but at least two answers to this question. The first is cosmology and astrophysics. I think goes at the heart of what it is to be curious about the universe, and that is something that it ticks inside us, that makes us human, and rekindling and keeping alive this curiosity for how the universe works, where it comes from, and what is our place in it is one of the fundamental reasons for doing this research. And I believe that the answers to these questions are too important to be kept inside the closed walls of academia. They concern us all, and therefore they should be shared with the widest possible public. Not least because it is the public who are funding our research through their taxes. And so we have a duty as scientists to share the excitement and the insights. On the other side of this question, the kind of applications and benefit to society, again, I think there's perhaps a perception that cosmology, astrophysics, fundamental physics are disconnected from reality because they're too far away, too exotic, too exoteric, even perhaps, to have any bearing on real life. But if you look at the history of science, actually, fundamental research in astronomy has changed the world many times in the past. And in fact, so much so that I'm writing a new book precisely on this topic. But more importantly, today, the kind of methods that we are developing in AI and machine learning to solve astrophysical problems have very important and very practical applications to societal problems as well, because although the data and the questions differ, the methods and the tools are very similar. So in fact, we are already seeing major developments in machine learning that are driven by cosmology, because we can't use machine learning tools off the shelf. We need to develop our own. The existing tools sometimes are not good enough for the kind of massive jobs we need to do. And therefore, our research is having an immediate impact on AI, and that trickles down very quickly to very practical applications.
Thank you, Roberto. Now, we've got a very timely question with all that's going on at the moment from, I believe, from Paul. There was some news recently about satellite constellations ruining our view from the ground. I believe this might be to do with Starlink and I can't remember. I should know his name, Elon Musk, and he's getting his chain of satellites. So is it true that this is going to ruin our view from the ground, and can we fix it? So no pressure.
Unfortunately, it is true. And if you, again, find yourself in a dark spot and you look up at the sky, even today, you can't fail to spot bright, fast-moving dots in the sky that are part of this constellation of low Earth orbit satellites that are designed to beam internet back to the ground. And that is a major problem both for professional and amateur astronomers. And it's a major problem for two reasons. The first is that you can't get away from them. If you are in London or in any big city, you got light pollution, but if you yearn for dark skies, you go to the Lake District or you go to another dark spot and you can still get to enjoy the Milky Way in all its glory. But this Starlink constellation, once deployed, will be composed of thousands of satellites all over the globe, and there is no escape. unless you go to space yourself, you don't get a clear, pristine view of the universe anymore, which spoils our enjoyment of the heavens as amateur astronomers. But for the professionals, this really endangers multi-billion-dollar observatories, because those Starlink satellites, as they pass in front of the telescopes, they leave trails in front of the cameras, which are very expensive to clean up and almost impossible, in fact, to do so perfectly. So no amount of machine learning and artificial intelligence can clean up the trails left by these passing satellites. And this really is a major danger that risks compromising our ability to push the frontiers of research from the ground because of this problem. So I'm very concerned about this. And I don't think that the solutions that have been proposed to date have worked very well. They're mitigating a little bit the problem, but in fact, every day we hear news of new constellations going up, the space race intensifying, new billionaires wanting to have their own constellation up there, and then we're going to make the problem really, really difficult for us in the future.
Thank you, Roberto. So we've got our most popular question so far. Actually, it's gone up a bit, and you may have answered this, so I don't believe you did, but it's from Keith. So it says, which does Roberto think is more likely, that dark matter exists, or that we will need a new understanding of how gravity acts over large distances? What idea excites you more?
That's a great question. And in fact, there's two camps, dark matter versus modified gravity, have been sort of fighting with each other for decades now, and certainly no one is giving up until and unless dark matter is found, or else disproved totally, which is exactly how science should proceed. I think there are very good reasons for believing in dark matter as a particle, perhaps left over from the Big Bang, or perhaps some other mechanism. Reasons that go beyond astronomy. There are reasons that are grounded in particle physics as well. There are theories of particle physics like supersymmetry, for example, that predict, in fact, dark matter with the right properties. So from a symmetry and beauty perspective, it's a very enticing proposition that one particle predicted from a particle physics theory ought to also have exactly the properties you need to explain what we see totally independently in the universe. I'm not so keen on modified gravity personally, because the evidence that I've seen points towards modified gravity not being able to explain the data, and eventually science has to account for the data. And while some data can be accounted for by modified gravity theories, not all of the observations we have about the universe can. And so ultimately it is an observational matter. Does this theory agree with what we see in the sky or not? And the evidence presently is against it. So my money remains on dark matter as a particle. Whether or not we will detect it in the next 10 years is a very difficult question, because it's perfectly possible that dark matter is a particle with such properties that we will never detect it in the lab, we will never produce it at the Large Hadron Collider, and we will forever remain with this unresolved mystery. But eventually science has to confront data, and that's where the ultimate answer has to come from.
Thank you, Roberto. So we've got another question here from Ben. Hopefully this isn't too tricky for you. Can you comment on the recent evidence from the Hubble lensing data that dark matter in galaxy clusters has a more clumpy distribution than expected? If true, does this have an impact on your own research?
Yes, that was a very interesting piece of research that came out very recently, in fact, and I haven't had the time to study it in great detail. I skimmed the result, and it did look very interesting, because it contradicted our sort of naive expectations of how dark matter ought to be distributed. Having said that, I think we are already, we have been going beyond the simplest explanations of how, or expectations of how dark matter ought to be distributed in the universe. We now know that we need to take into account a lot of much more subtle effects in predicting the dark matter distribution in clusters, for example, baryonic feedback and explosions of supernovae, and other dirty physics to do with the hydrodynamics of how things coalesce and so on and so forth, that we weren't able to take into account in the past, because the computer power available didn't stretch all the way to being able to model properly this minute but very important on small scales effect. So I think we're seeing here the first inroads from the observational side, or very important inroads, into upping our game from the theory side and improving our predictions, our computational ability, much of which also benefits from machine learning in the form of accelerating the computations by smart use of AI. And so the observations are pushing us to develop better our theories to better understand whether or not the existing paradigm for dark matter can accommodate this kind of very accurate and very precise observations on even smaller scales.
Thank you. So there's another question that links into talking about machine learning. This is anonymous, and this is, what is the precise role of machine learning in the search for dark matter? What type of data is it analyzing, and what is it trying to identify, or what's it looking for in the data?
Great question, and that's a difficult one to answer because it really depends on the actual specific problem that you're deploying machine learning for. To give you but one example among many, looking at the shape of galaxies in the sky is a way of looking for dark matter that I haven't discussed today. But by looking at minute distortions in the shape of the galaxies and how they are common among galaxies that are close by, one can detect the gravitational effect of dark matter on the light from those galaxies as it travels through the universe. And this is called weak lensing. Now, this is very tricky, though, because first of all, you need to identify the galaxies, you need to measure the shape of the galaxies, and you need perhaps to clean up all the kind of effects that we discussed about trails of satellites in front of your camera. And on top of this is a small effect. It can easily be confused for something else. What's happening now is that with the new generation of telescopes like the Vera Rubin Observatory that I mentioned, we're going to get hundreds of thousands of images of galaxies a year, and it won't be possible to see them all. No human eye will ever be able to inspect those galaxies, and therefore we need automated means of detecting the shapes. And not all galaxies are the same, of course. We have spiral galaxies, edge-on galaxies, elliptical galaxies, etc., etc. We need smart algorithms that would be able to do the job that once upon a time we would have asked grad students to do, and nowadays we can't because there are enough grad students to do it, even if we wanted to. And that is one arena where machine learning is leading the way, because we simply cannot do the job without machine learning.
Thank you very much. Talking about students, actually, because you've provoked a lot of interest in your field here. So we've got an MSc student in AI, Alistair, writing in saying, how can someone get involved in your area of work? How would, what, I suppose he's asking, what career path would you get into to actually end up working in this field? So hopefully you'd be able to answer that, please, Roberto.
Yeah, great question, Alistair. I think we're seeing more and more now the fact that astrophysics and cosmology teams are cross-disciplinary now. So we have astrophysicists, we have theoreticians, we have particle physicists, and we have machine learning computer science experts who help with the method development. We often see papers, for example, co-authored with people from DeepMind, for example, and other places like that, whose job is not astrophysics, but whose primary job is AI and machine learning. So we really see this coming together of the communities, with the astrophysicists providing expertise about the data and the problem and the physics, and computer scientists, machine learning experts providing cutting-edge insights into those systems. And so if you come from that side of the equation, it's relatively easy, I would imagine, to offer you services for a project, and I'm sure you will be welcomed with open arms, because there is a real need for new insights, new ideas from our community. And I think it's really valuable to see these two different communities of experts working together and producing something that neither of the two communities could do on their own, because it requires true insights about both astrophysics and the machine learning computer science aspects. And so I would definitely encourage you to sort of dip your toes in the water by doing a little project, perhaps in collaboration with a researcher or a professor working in the field, and that will give you a taste for it and also will showcase your abilities.
Thank you very much. A question here from Sarah, which I'm often asked, and it's always a popular question. The universe is expanding, but what is it expanding into? And I suppose, and also on that topic, there's a double question here on what caused the Big Bang, which is I don't know if you've got time to actually answer that, but brilliant question.
Brilliant, brilliant, and always a very difficult one in terms of what is the universe expanding into. I think the difficulty with this is that our imagination is somewhat limited, and so we, myself included, we imagine the universe as an expanding balloon, perhaps with pennies stuck on top. And I use that metaphor and analogy often. I prefer the one of the expanding pizza dough, being a food lover, but it's the same fallacy. So we imagine this expanding balloon, and it expands into three-dimensional space, and therefore surely the universe must be expanding into something else. Unfortunately, though, for our imagination, that is not necessarily the case. The data that we have about the universe tell us that the universe, insofar as we can tell, is infinite in spatial extent. So an infinite universe grows bigger, locally grows bigger, that every distance to everything else grows bigger, but it doesn't grow into anything. One, because it's infinite, and therefore, there cannot be any outside to an infinite universe. And two, because an infinite universe always has been infinite. So all you can say is that my distance from this point in space to another point in space is growing, and that is true of every point in space. But you can never take the outside view. You can never step outside the universe in a higher dimension and look at it from the outside like you would do with the growing balloon, because there is no such additional dimension, and therefore we are stuck imagining this universe becoming bigger, but we can't even pose in a meaningful way the question of what is it expanding into, because there is no extra dimension into which the universe expands. And so I know this is a little bit unsatisfactory, but that's all we can really say about it. What caused the Big Bang? That's an easy one. We don't know. That's a difficult one, but an easy one to answer. We really don't know.
Brilliant. So we've got a question here, anonymous question. It's got 4 thumbs up. Has a recent detection of high energy cosmic neutrinos by Anita in Antarctica, does that indicate there could be condensed dark matter inside the Earth's core?
Well, that's another exciting avenue for dark matter research. Which I haven't had time to talk about, but indeed, if dark matter meets and annihilates either in the core of the sun or indeed in the core of the Earth, then this will emit other kind of particles, including neutrinos, which are the only particles that can escape either the core of the sun or the core of the Earth. So if those neutrinos escape and we can detect them with enough confidence, then we can say that actually we've used an invisible particle, the neutrino, as a telltale sign for another invisible particle, the dark matter, or almost invisible. So that would be a really exciting avenue to discover dark matter. So that's the backdrop to the question. As for the neutrinos detected recently, I think the energy of those neutrinos is rather too high to be attributable in a straightforward manner to dark matter. It depends on the dark matter mass, the dark matter characteristics, and so on. And also the neutrinos from the core of the Earth are a rather weak signal. So if you, in most dark matter models, if you see neutrinos from the Earth, you'd expect to see neutrinos from the sun as well, which is further away, but ought to have a much bigger neutrino content than the Earth, simply because of its higher mass. So again, it's a tantalizing hint, but as with much in dark matter research, is not conclusive yet. Brilliant.
So unfortunately, we've come to our last question now because we're running out of time. So we've got a popular question here from Fatima. And this is actually always, I think, links on about how AI is kind of seen and understood by everyone, really. And so the question is, will AI come up with theories on the universe on its own, or will it be entirely factual? So I suppose, will it just answer our questions, or will it actually, I suppose, start, coming up with a mind of its own and start having its own ideas? So I don't know if we've got time to answer that fully, hopefully, Roberto, of only a couple of minutes, but over to you.
Okay, I'll do my best in 2 minutes. It's a great question. Thank you, Anita. And yeah, it would deserve much more time. But in a nutshell, I think it's true that AI so far has given us answers to questions that we posed. So we essentially program the AI to give us specific answers to specific questions. But it's rather different, and this goes back to what I was saying before about the virtuous circle between astrophysics and AI. It's rather different in astrophysics than it is, say, in autonomous driving cars, because an AI that decides how to drive a car on a road it doesn't really need to come up with an explanation for its behavior as long as this behavior is good. As long as it does what it's supposed to do, it doesn't come off the road or causes an incident. We don't care how the AI gets to this conclusion. But in physics and in astrophysics, we care a great deal about what the AI is thinking, quote unquote, because what we're after is a physical explanation for the data, not just a description or good prediction, but explanations. So this is the topic of explainable AI. How do the AIs come up with their answers? And it's very important for us in physics and astrophysics. And very recently, some of my colleagues have started making inroads into this question by demonstrating that certain kind of AI trained in a certain way can come up with their autonomous discovery of physical laws or rediscovery of gravity laws, for example. So we're moving towards a future where AI won't just describe the data, but will be able to actually come up with equations and eventually theorems or physical laws that we ourselves could not have discovered or had not discovered before. So in this respect, I think there is a path to creativity for AI, and it's a path that's very much tied to the physical nature of our problems, which is rather different from the kind of problems that are otherwise faced or posed in other fields. And again, a very interesting, very challenging field for AI in cosmology.
Well, thank you very much, Roberto, for that answer there. Unfortunately, we've come to an end there. We've got plenty more questions, but I think we do have to draw a line under it somewhere. So firstly, can I please have a virtual round of applause for Professor Trotta and his wonderful talk there and going through his answers as well. That was absolutely amazing. Science Breaks is continuing. We've got plenty more talks coming up. I think there's a slide here. So thank you very much for joining us for this Science Breaks. I believe the next talk is on Thursday, the 1st of October, and that's Professor Robert Endres, and he will be talking about how cells perceive their environment. After that, we've got Professor Gareth Collins, the dinosaur dooming asteroid, and Professor Cristina Lo Celso, the bloody battle against leukemia, which is on Thursday, the 15th of October. As I say, it's been a pleasure speaking to you all, and it's been wonderful to be able to join Roberto. One of the big, well, many of us have had to endure through lockdown is that we haven't been able to visit the department, and no longer, I don't unfortunately get to meet up with Roberto and have a nice chat with him and bump into him in the corridor, which I miss immensely. So it's been a real pleasure being able to catch up with him today and listen to him talk. So thank you very much for joining us. Hopefully you'll be able to join us for our next event on Thursday, 1st of October. And once again, and finally, a big round of applause, please, for Roberto. Thank you very much. And I believe that's where, unfortunately, we will be ending today's session. So thank you.